So, we continue with tensors, and this would be the last lecture on tensors, after which we actually move on to the primary topic of this course, which is fluid mechanics. So, during the last lecture, we saw examples of what symmetric antisymmetric tensors would be. All tensors are not necessarily symmetric or antisymmetric, but they could be written as a linear combination of a symmetric and antisymmetric tensor. And this, as I mentioned earlier, is a very useful decomposition that is soon going to be relevant when we think in terms of deformation of a fluid. Besides that, we also encountered an idea of isotropy. The isotropy concept tells us that if I am thinking of it, that if I were to make measurements, there were no preferred directions. No angle, no direction is preferred over the other. Mathematically, isotropy means that when I have done these transformations, so let's say I have done it for a vector where a transform vector can be written in terms of the components of a transform vector in a rotated coordinate system, can be written in terms of the components in the old coordinate system in this manner. And similarly, if I have a tensor, let's call it T, then the tensor also undergoes a transformation of the following form. Now, isotropy tells us that when you have this transformation, a rotation, in that particular case, the components of the tensor don't change. That's the idea of isotropy. And so, we saw examples of isotropy. So, when I have 0th order, which is nothing but scalars, all scalars are isotropic. If I go to first order, which is vector, no vector is isotropic. When I say no vector, I am basically excluding the trivial answer, which is that null vector is isotropic. Null vector is a vector whose all components are 0, and this would be true for any order. For any order, if you take a null tensor, it will always remain isotropic trivially, because whenever you apply the coordinate transformation, 0 will transform to 0 itself. When you move to second order, then the Kronecker delta, which you could write it as delta or the identity tensor I, either way, which has components that are given by delta ij, which is 1 if I is equal to j, and I not being equal to j gives us 0. This is an isotropic tensor. When we move to third order, then I have the permutation symbol, which is also known as the Levi-Civita symbol or Levi-Civita tensor. The permutation symbol has 3 indices I, j and k. It picks up a +1 value if I, j, k took all cyclic values, which is to say that values like 1, 2, 3, then 2, 3, 1 or 3, 1, 2. It picked up a -1 value if the indices I, j, k were to take anticyclic values. So, 2, 1, 3 or 1, 3, 2 or 3, 2, 1. So, cyclic anticyclic is to say that this combination is your cyclic combination. So, you choose 1, 2, 3 or you choose 2, 3, 1 or you choose 3, 1, 2. They are basically in the same order, which is why they take values of +1, -1 depending on whether you move along the cyclic order or you move along the anticyclic order. And they take a value of 0 if the indices were repeated. So, repeated indices could be 1, 1, 2, 1, 1, 3, and you could also have all the 3 indices being the same. So, all combinations of indices where at least 2 indices are repeating, that gives me a value 0. So, that is basically revising what the definitions are for the permutation symbol. So, that is your third order isotropic tensor. For fourth order, and actually for any order higher, the isotropic tensors are combinations or products of the lower order isotropic tensors. So, when I say that, if I label a fourth order isotropic tensor with the letter A, so it has 4 indices I, J, K, L. This is a combination of delta Ij, delta Kl, delta Ik, delta Jl, delta Il, delta Jk. So, this is what you have as the combination of the order 2 tensors, giving us products of order 2 tensor, which gives me the fourth order isotropic tensor. Now, you could think of a combination where you have epsilon I j k with a vector A L. Now, the requirement of isotropy is that each of these should be isotropic. Now, epsilon I j k is isotropic, so we are good. But what is a vector that is isotropic? That's my null vector. So, which means that this combination, even though it's a legitimate way of writing it tensorially, it doesn't appear because the only isotropic vector is the null vector. So, I don't have something that appears here in terms of epsilon I j k. So, this makes our life quite easy, and we are going to, as I say, primarily restrict ourselves to the till order 4, because that's mostly what you will see in this course. The largest order of tensor that you will encounter would be an order 4 tensor. Now, the question that naturally arises, how does this help us in doing any calculation using this kind of tensor analysis? How does this benefit? So, we will do some integrations to start with. So, we are interested in an integral of the unit normal. So, the unit normal is the vector that is pointing from the surface that is drawn, and here I am interested in a sphere of unit radius. So, n is the unit normal to this sphere, which if you write in terms of spherical coordinates in its Cartesian coordinate, but expressed in terms of the polar angles, it would be cosine theta, sin theta, cosine phi, sin theta, sin phi. So, for a sphere, this would be the unit normal to that particular surface. Now, if you want to do this integral over the surface of the sphere has unit radius, which means this can be written as, so this would be r square d omega, r being the radius, which in this case is 1, and d omega is the solid angle, which is sin theta, d theta, d phi. So, if you do this, you need to do 3 integrals: an integral over cos theta, which is nx d omega, that should be integral cos theta, sin theta, d theta, d phi. There is a double integral. Now, integral sin theta cos theta, theta running from 0 to pi and phi running from 0 to 2 pi would give you 0. Similarly, when you do the integral over ny d omega, there is a cosine phi here. So, when you integrate it over phi, that would be 0, and the same would be applicable if you were to do an integral over nz. Now, why am I doing all these trigonometric integral? Because now you see that the object that we are interested in is an integral of this unit normal over the surface of a sphere. A sphere is an isotropic object. So, whatever I obtain should actually be an isotropic quantity. And I see from the LHS that the object on the left is a vector, which means on the right I should get a vector that is isotropic. And we just learned that the only isotropic vector is the null vector. So, without explicitly doing the 3 integrals, the trigonometric integrals, you have arrived at this answer. But again, it was not a huge advantage in terms of calculation time. What if I am trying to do an integral of this object? This nn is in index notation ni nj. It's known as a dyad. It's a second order tensor involving the two unit normal. So, you will have terms like nx square, nx ny, nx nz. If you think in terms of matrices, ny nx, ny square, ny nz, nz nx, nz ny, nz square. So, it has 9 components which you now need to integrate over this unit normal. And we are not going to try doing this integral using trigonometry. We are going to use the property that whatever I am doing, I am basically integrating this over the surface of the sphere. So, once again just reminding, I have this unit normal, I am integrating over a sphere. I expect the final answer to be an isotropic order 2 tensor. So, the expectation is that because the LHS is integrated over the surface of the sphere and it is of order 2, I should have order 2 isotropic tensor that should come here. Now, what is an order 2 isotropic tensor? So, an order 2 isotropic tensor would be my Kronecker delta. But then I can take any isotropic tensor and multiply it with a scalar and it continues to remain isotropic, because the scalar is any scalar is always isotropic, and a scalar multiplying any order vector or any order tensor gives me the same order. So, a constant c, some scalar multiplying a vector continues to remain order 1. A constant c, some arbitrary constant c multiplying any tensor continues to give me that same order. So, the order does not change and the isotropy does not change. So, what I have now is I have that this integral which actually involves doing integration over 9 components. So, there are 9 components of this order 2 tensor. So, I need to do 9 integrals. So, instead of doing 9 integrals, I have realized that the symmetry of the problem, the fact that you are dealing with an isotropic quantity, immediately tells you that there is only one constant that is there in the problem. You do not need to do all the 9. And do we really need to do all 9? So, let us take one example. So, I will say I is equal to j. So, if I is equal to j, ni nj becomes ni ni or nj nj. There is nothing sacred, as I keep saying, if the indices are repeating. So, when I is equal to j, well, ni nj is not equal to ni ni. So, this, let me just make sure that it is not, yeah. So, ni nj, if I is equal to j, is ni ni or nj nj. The definition was this is a unit normal. Unit normal means the magnitude of that particular vector is going to be 1. So, which means this is 1. Nx square plus ny square plus nz square is equal to 1 if you write in Cartesian. The length is always 1, which means if I is equal to j, the left hand side is ni square d omega, which is integral d omega, and d omega is sin theta d theta d phi, theta going from 0 to pi, phi going from 0 to 2 pi. So, it is the integral of the entire solid angle of for a sphere, which is 4 pi. The RHS is the constant delta II. Now, what is delta II? Delta II is, by Einstein notation, delta 1 1, delta 2 2 plus delta 3 3. This is 1 plus 1 plus 1 is equal to 3. Another way of thinking of this quantity, that delta with repeated indices, or for that matter for any matrix, is the trace of that particular order 2 tensor. So, if you have any tensor A, the trace of that particular quantity is going to be AKK, and we already have had this pact, we have agreed on this, that whenever you have repeated indices, the indices are going to run over the dimension. So, if it is 3 dimension, it is going to be A11 plus A22 plus A33. If it was 2 dimension, it would be A11 plus A22. So, for an identity matrix or an identity tensor, the diagonal elements are 1, 1, 1. So, when you sum them, you basically get 3. So, this becomes a constant times 3. So, equating the LHS and RHS, you find that the constant is 4 pi by 3, which means instead of doing those 9 integrals, you have now arrived at the conclusion that you have 4 pi by 3 delta ij. So, this you can keep being more adventurous and start doing higher and higher order. So, for instance, you can now say that I have, instead of an order 2 tensor, I have an order 3 tensor. And we know that an order 3 tensor that is isotropic is going to be epsilon I j k. So, this is the, instead of having 3 indices contributing to 27 integrals. So, here you are actually supposed to do 27 integrals. You automatically reduce this to saying that, hey, the object that I am integrating should be isotropic, and there is only one isotropic tensor that I know for order 3, which is the permutation symbol, and this should be the answer. What further can we say? Now, we realize that on the left hand side, Ni, Nj, Nk can be written as Nj, Ni, Nk. There is nothing particular about the order in which I am writing them, which means that the integral that is there on the LHS is symmetric about I and j. But on the right hand side, epsilon ijk is negative of epsilon jik. This is an antisymmetric tensor, which means that if the left hand side is symmetric about the indices I and j, and the right hand side is antisymmetric about the indices I and j, the only way you can reconcile this fact is if the constant was to be 0, which means this entire integral turns out to be 0. So, without doing any integration, without actually carrying forward any trigonometric integration, you have used the property of symmetry or antisymmetry and isotropy, and you have managed to do this integration. The last bit of adventure, we go to an integration that is over 4 indices, Ni, Nj, Nk, Nl. And we saw earlier that this is an order 4 tensor, which is isotropic, which means that the only isotropic tensor that is allowed is a combination of the order 2 tensors. So, this now tells us that I have reduced what could have been 81 trigonometric integrals to actually finding 3 constants. Now, can we reduce this further? So, if I now look at this, Ni Nj is the same as Nj Ni, which means that the integral on the left hand side is symmetric about I and j. Now, let us inspect the terms. The first term is symmetric about I and j. So, C1 delta ji is the same as C1 delta ij. So, this is symmetric. For the next term, if I switch I from j, I get delta jk delta il, which is not the same as what was originally. So, this is not symmetric. And the last one is delta jl delta ik, and this also is not the same as what we started from. So, that is also not symmetric. So, we have on the right hand side one term being symmetric about I and j, and the other two are not symmetric. But there is a solution. The solution is, if you look at what you got by flipping the indices of the term, the second term, you get back what is actually the third term. So, this is nothing but the third term, but with a different constant. And what you got by flipping the indices of the third term is nothing but the second term, but with a different constant. So, the solution is this has to be the same constant. Now, the bracketed term is symmetric about I and j, and the same applies for the first term, that anyway was symmetric about I and j. Let us now check what about, let us say, j and k. If I take j and k, Ni, Nj, Nk, Nl, if I flip the indices, it's the same. There is a symmetry about j and k. So now when I am flipping about j and k, so if I switch indices between, so swap j and k. So this becomes constant ik jl, this becomes jk il, and this one delta il delta jk, or rather you could write it as delta kj. So this term is already symmetric about j and k, whereas these terms are not symmetric about j and k. But there is a solution. You look at this particular term delta jk delta il, and I have delta ik delta jl. Once again, if I compare the terms, if I choose the same constant delta ij delta kl delta ik delta jl delta il delta jk. So if I have the indices now actually being switched, so this again this should have been, so this should be ij and this should be kl. Now it's all right. So I have delta ij delta kl. So finally you see that this is the same as what I have here, this is the same as what I have here, which means C1 should be equal to C2. So I'm calling that by one single constant. So finally what I have here is that integral ni nj nk nl d omega is a constant delta ij delta kl delta ik delta jl delta il delta jk. Now how do I find the constant? You can basically apply the same idea, that let's choose I equal to j, k equal to l. If I do that, then this becomes ni square nk square d omega, which again we saw earlier is 1 times 1 d omega, they are unit normal, so it becomes 4 pi. On the right hand side, so this is LHS, on the right hand side I have the constant delta ij becomes delta ii, delta kl becomes delta kk, delta ik becomes delta jk, and then jl you can write once again as delta jk, and delta il you can write as delta jl, delta jk becomes jl. You have a freedom of what you are switching. So basically you are saying I is equal to j. So what I did here, I made this as j and I left L by itself, and here j was left by itself and k was basically switched to L. You could have done the other way. You could have said I is left by itself, L basically becomes k. So j is now switched to I and k is left by itself. So it's one and the same. You could write this as delta ik delta ik. Now delta ii, as we saw earlier, is the trace of the identity tensor, so it should be 3. Delta kk is also the identity tensor, so that should also be 3. Delta jk, so this is delta jk delta jk. So it's a scalar. I can switch either of these indices, so I can write this as delta jj or delta kk, and that is equal to 3. And similarly the last one is also equal to 3. So this becomes 15 times c. So here the constant that we have now becomes 4 pi by 15. So this entire thing was done once again by using ideas of symmetry and isotropy, and we are able to actually find out what these constants are. Now, besides being mathematically interesting, is there any merit in doing these kind of calculations? So we will see some of these at play. So, especially when we are trying to actually compute quantities like this, Ni d omega, Ni Nj d omega, Ni Nj Nk, Nk Nl d omega. Quantities like this often appear when you are trying to calculate things like drag, or you are trying to actually find quantities like how does viscosity change when the fluid has some particles in it. So, when you are trying to find suspension viscosity, or when you are trying to calculate the drag or the forces on the object, that's when you will encounter integrals like this. So, we are not yet there to do any calculation of that sort. This is the suspension viscosity we are not going to touch upon, but these are the higher order unit normal integrals, where instead of doing those integrals explicitly, which would have been quite an arduous process. So, instead of doing those 81 integrals, you can quickly just come up with this answer. We will use one more very important relation using this idea of isotropy. So, as I said that if you take a dot product of, let us say, two vectors, you arrive at scalar. If you now say, so this is ai bi in index notation. Now, if you take an order 2 tensor, dot it with a vector, you end up getting a vector. So, I will have aij bj, it eventually ends up being a vector. You can take a dot product of an order 2 tensor with another order 2 tensor, and this gives me another order 2 tensor. So, this would be aik bkj. This is your classic matrix multiplication. Now, A double dotted with B is a new thing. This is not your standard matrix multiplication. This is, whenever you are dotting, what you do is, if you look at it, you had an object of order 1, another object of order 2. So, you brought about two objects which together between them have two orders. Every dot product is going to reduce two orders in the final answer. So, you had an order 1 object with another order 1 object. When you did the dot product, you got a scalar. This is something which you know, but we are now viewing it in terms of what the dot product does. When you dot the order 2 tensor with a vector, you are dealing with 3 indices in total. Doing the dot product gives you a vector. You have reduced from 3 minus 2, you get 1. When you are dealing with 2 order 2 tensors, you are actually playing around with 4 indices. So, this has 2 indices and the B also has 2 indices. So, finally, when you reduce 2, you get back an order 2 tensor. When you now do a double dot product, you are doing a double dot product or a double contraction. So, the reason why you use the word contraction is because you are getting rid of indices. So, when you are doing a double contraction here, this is going to be 2 indices coming from A, 2 indices coming from B. You are working with 4 indices, but then you have the contraction happening twice, which means finally what you would get would be a 0th order object, which is a scalar. So, how does this look like? This is aik times bki. So, you first do a contraction with the indices that are inner and then you do it for the outer. You have to remember, this is not the same as aik bik, even though this also is a scalar. This is also a scalar, just like what you have here. In general, they are not equal, because aik bik, if I write in terms of the bold notation, this is going to be A double contracted with B transpose. Okay. So, this is something that is important, that you need to actually understand that, or you could write this as B, sorry, yeah, B double dotted with A transpose, because this would be B I K and then it would be A transposes K I, which is B I K A I K. So, they are different. The only case where, and whereas here this one is A double dotted with B. So, the only case where they would become the same is if, let us say, one of these order 2 tensor was, it would turn out to be equal here if you had is symmetric, right. So, this is what we have, we are doing, playing around with all these kind of double contractions. Now, let us go a little further in exercise. So, let us take an order 3 tensor and dot it with a vector. So, when we do an order 3 tensor dotted with a vector, once again you see that here you have 3 indices, here you have 1 indices. So, with that, now whatever you are going to obtain is going to be an order 2 tensor. So, written in notation, this is Qijk AK. So, this is a dot product that is occurring between a higher order tensor, which is order 3, and the vector. Now, you can continue this further, and let us say now you do this dot with an order 2. By now, you are starting to get a feel for it, what you are going to get. So, you have an object that is here that has 3 indices, an object that has 2 indices, and then when you do the dot product, you are going to now get something that has 3 indices. So, it would be Qijk AKL, which is PIJL. We are nearing this exercise. If I now do this, I am doing a dot product or a contraction between 2 order 3 tensors. So, I have 3 coming from Q, 3 coming from P. A single dot product would give me an object that is a 4th order tensor. Now, we have encountered an order 3 tensor, which is the Levi-Civita symbol or the permutation symbol. What would this object be? Let us try to see. Now, this in index notation is Ijk KLM. You have to again remember, now when you are working with more number of indices, that the dot product or the contraction is always going to work on the innermost indices or the closest indices between the two. Now, we already know that this final object should be a tensor that has 4 indices or a 4th order tensor, delta IJLM. But can we say something more? Now, on the left hand side, I am dealing with a tensor that is a product of 2 isotropic tensors. Epsilon ijk is isotropic, epsilon klm is also isotropic, which means what I have here on the right hand side should also be isotropic. If the LHS is isotropic, the RHS should also be isotropic. Products of isotropic tensors would also be isotropic, which means we have already seen what is a 4th order isotropic tensor. There is nothing new as a 4th order isotropic tensor. It is a combination of delta ij, delta kl, delta il, delta jk, delta ik, delta jl. That is the only possibility. I do not have anything else to work with. Can we say a little bit more? Well, we can say one thing for sure, that epsilon ijk is antisymmetric about I and j. It has an antisymmetry. And here delta ij is symmetric about I and j. So, if delta ij is symmetric about I and j, and here this is antisymmetric about I and j, the only way that this can be made to work is, one sec, I think I have jumped here once more. Let me just write this carefully. Epsilon ijk, epsilon klm, which is an isotropic tensor in ijlm. So, it should be in ijlm. So, that is delta ij delta lm, delta il delta jm, delta im delta jl. So, you saw also an instance of how errors appear in index notation. So, what I was doing, I brought in k on the right hand side, whereas k was a repeated index. This actually has a summation of k running from 1 to 3. So, on the right hand side, I have to work with all the free indices. So, the free indices in this problem is I, j, l, m. K is not a free index. So, what I cannot have is k appearing on the right hand side. Okay, now let us go back to it. So, the LHS is antisymmetric about I and j, which means if I switch indices, this becomes jik klm. But delta ij is symmetric about I and j. So, this continues to remain delta ji delta lm, which is one and the same. So, this is not possible. You cannot have the LHS be antisymmetric about I and j and the RHS being symmetric about I and j. So, the only way that can work is if that term was, if C1 was 0. So, what we have concluded is that epsilon ijk epsilon klm is a constant C2 delta IL delta Jm plus another constant delta Im delta Jl. Now, let us see about flipping other indices. So, we saw that this was antisymmetric about I and j. So, this becomes minus jik klm. So, if I do that, this becomes, if I switch jl im plus jm il. So, now if you observe, the LHS is changed to minus epsilon jik klm, and in the RHS you have right now, when on switching indices, you have C2 delta jl delta im plus C3 delta jm delta il. Now, what I can further do is, if I write this out on the right hand side, so jik epsilon klm delta jl delta im jm delta il. So, now if I take the negative sign to the other side, I have minus C2 delta jl delta im minus C3 delta jm delta il. Now, I can play with the indices once more. What I can try doing is, I can do the same exercise that I have here also for lm. So, if I do this for lm, I have jik and then I have kml. This is going to pick up a negative sign, and here I have minus C2 delta Jm delta IL, and this one is delta L, so I am switching between L and M, so delta JL delta IM. So now if you look at, and then if you stare at the two expressions that you have C2 delta JL delta IM here, you have here C3 delta JL delta IM, and for the other expression C3 delta JM delta IL, and here you have C2 delta JM delta IL. So if we are trying to actually work out what these indices would be, now going back to what my indices are. So I have epsilon JIK, epsilon KML is equal to C2 delta JM delta IL plus C3 delta JL delta IM. So now if I try to find out what these constants actually are, I can subtract these two equations and then choose the value of some indices. So I can choose values of IL, JM, etc. So if I do that, I'll get C2 to be actually 1 and C3 to be minus 1. So finally what I have is epsilon ijk, epsilon klm is delta IL delta JM minus delta IM delta JL. So this is a very important relation. It relates the product of two permutation symbol with a product of Kronecker delta. Now how do we use this? So we have now almost everything that we need in order to proceed and try few vector calculus identities. So with all that we have, we will go about proving few vector calculus identities. So the first thing we will do is we will calculate the curl of a gradient. Now this we know is 0, and let's try to see what can we show that using index notation. So gradient of a scalar phi is going to be dou phi dou, if this is the kth component, then this would be dou phi dou xk, and curl of any vector, let's say the vector is B, is going to be epsilon ijk dou xj of bk, and here for me B is gradient phi. So if I write this out, I have epsilon ijk dou xj of dou phi dou xk. If I switch the indices, I could write it as dou square phi dou xk dou xj. So if you see the derivative here, dou xk dou xj, this is symmetric about j and k, whereas epsilon ijk is antisymmetric with j and k. So what you have here, you have a double dot product of an antisymmetric tensor with a symmetric tensor. So f is dou square phi dou xk dou xj, so it is symmetric about j and k, and epsilon is antisymmetric about j and k. So this we have already shown earlier is going to be 0. You can, because the indices are repeated over j and k, if you switch indices, this becomes epsilon I kj, and this remains unchanged. There is no change for this particular quantity. Now you could call k and j with switching what you call them, because they are they are repeated indices. So you can call k as j and k, and you will get back the same thing. So you will find that a vector is equal to negative of itself, which has an only answer, which is the null vector. So that's the proof for this quantity. Similarly, divergence of a curl. This also is an identity that is 0. Now, if you have to prove this, curl of a vector, its ith component, is epsilon ijk dou ak dou xj. If I now do a divergence of this, I am expecting a scalar here, which would be dou xi of epsilon ijk dou ak dou xj. Now, the permutation symbol is a constant tensor. It does not have any spatial dependence. So, I can take it outside the derivative and I am left with dou square xa dou xi dou xj. Now, this is antisymmetric about I and j, whereas the derivative, so epsilon ijk is antisymmetric about I and j, whereas this is symmetric about I and j. So, if you consider I and j, I once again am dealing with a quantity that is a double contraction of an antisymmetric tensor and a symmetric tensor. So, it again turns out to be 0. So, this you can keep doing for different cases. For instance, you can take something which is even more complicated, which you may not always, because the key idea is you do not necessarily always know what are the vector calculus identities unless you look it up. So, how do you do this? So, this is something which is again going to appear in momentum equation. I am taking curl of a curl. So, what is curl of a curl? So, let us go forward. This has the ith component. So, let us try to find curl of a curl is going to be, the ith component is epsilon ijk dou xj and the kth component of curl of A. Now, what is the kth component of curl of A? The kth component of curl of A is klm dou am dou xl. Now, here you just pay attention to one thing, is that I am choosing different letters for the repeated indices than what I have already used so far. I do not want to use ij here because I have already used I and j earlier. So, when I am trying to find the kth component of curl of A, I am using L and M. So, finally, what do we have here is epsilon ijk dou xj epsilon klm dou am dou xl, and then this becomes ijk klm dou square am dou xj dou xl. Now, we just saw this identity. The epsilon ijk epsilon klm is delta il delta jm minus delta im delta jl, and this then gives me, operating on the first term, I have delta il delta jm dou square am dou xj dou xl, and on the second term it is delta im delta jl dou square am dou xj dou xl. So, here I will replace j with m because delta jm dou xj becomes dou xm and delta il dou xl becomes dou xi. So, this is what the first term is. For the second term, I have j replaced with L. So, I have this term becoming dou square dou xj square or dou square dou xl square, it does not matter. So, that is basically dou xl xl or dou square dou xj dou xj, and then m becomes I. So, this is now finally dou xm of dou am dou xi minus dou square dou xj square ai. Now, I can take the derivative inside and bring the dou xi outside. So, I have dou am dou xm minus dou square dou xj square ai. So, this is what we started out from. Now, if you look at these two terms, the first one is actually a gradient of a divergence. The term inside the bracket is actually a divergence, and what you have outside is a gradient. So, divergence of a vector is a scalar, gradient of that scalar gives you the vector. So, this is the ith component of gradient of a divergence, whereas the second term is actually a Laplacian of a vector, that ith component. So, finally, you have here curl of a curl is gradient of divergence of a vector minus Laplacian of a vector. So, this is something that is quite useful. We are able to relate an identity without actually having to do a look back of how you get here, just using index notation.